Hello and welcome to our lesson on greatest common factors. So there are lots of practical applications for finding greatest common factors. We are going to be talking about greatest common factors to prepare for the work that we're going to be doing with fractions, which is technically another practical application of using and finding greatest common factors. But let's talk about what it is, and then later we'll see how it's going to be useful. So a greatest common factor is also called a greatest common divisor, and so we'll sometimes abbreviate greatest common factor as GCF, and then we'll also abbreviate it as a GCD because we can also call it a greatest common divisor. So a GCF or GCD, again, greatest common factor or greatest common divisor, is defined as the largest positive integer that is a factor of two or more integers. So it's the greatest, the largest, and it's a factor of two or more integers. Okay, so it's a factor that they have in common. Now, in simpler words, it's going to be the largest number that divides evenly into a set of integers. So sometimes we're going to be able to look at our numbers and just based on our experience with the numbers, we'll know what the greatest common factor is. For example, when I'm looking at 2, 6, and 8, I know that 2 is the biggest number that divides evenly into that set of numbers. So I can tell just by looking here that my GCF would be 2, or my GCD would be 2. Same for the next set of numbers for 5, 10, and 15. I know that the biggest number that divides evenly into that set of numbers is going to be 5. So I can say my GCF here would be 5. And then as the numbers get a little bigger, it's a little more difficult, again, depending on your experience and comfort level with the numbers. So when I'm looking at 8, 12, and 20, again, I can see that 4 is the biggest number that's going to divide evenly into that set of numbers. So here I would say that my GCF is going to be 4. Now, if it was a little harder for you to see that, or if in general it's hard for you to see what the biggest number is that will divide evenly into that set of numbers, I want to give you some strategies for calculating it. So one of the ways that we can actually calculate the GCF for a set of integers is to list out all of the factors of each of the integers and then just see on those lists what's the biggest one that they have in common. So let's make a list of all of the factors of each of our numbers and again find the biggest one in common on our lists. So let's start this one. We're looking for the GCF here for 16, 24, and 30. And again, if you can see it, great. If not, let's start by listing out the factors of 16. So I know obviously 1 is going to be a factor of everything, and it's important to list that in our factor list because sometimes 1 is the greatest common factor for a set of numbers. So we've got 1, it's divisible by 2, and not 3 but 4, not 5 or 6 or 7 but definitely 8, and then not 9, 10, 11, 12, 13, 14, or 15, but definitely 16. So there's the list of factors for 16. Let's make the list of factors for 24. So we can divide by 1, 2, 3, 4, 6, 8, 12, and of course itself. And now I'm going to run out of space, so let me just move this guy over. Now let me make my list of factors for 30, which is the last number on my list here. So I can divide by 1, or 2, or 3, or 5, or 6, 10, 15, and then 30. So I've got all the factors for each of my numbers, and then if I'm looking for the largest number that is in common to all of those lists, it's going to be 2. 2 is the biggest number I see that is on all 3 of those lists, the biggest factor that they have in common. So now I can say that the GCF here is going to be, and sometimes we use this notation, we could say the GCF for 16, 24, and 30 using notation that looks like this would be 2. Okay? Now that's not necessarily the most efficient way to do it, but if your numbers are small enough and finding those factors is easy, then maybe that's a process you can also do in your head. So it's good to see the process on paper because I think, again, that is something that we tend to try to do in our heads. Now we can also use prime factorizations, which we talked about in the previous lesson. I can find the prime factorization or prime factorizations for each of the numbers on my list, and then find the product of the prime factors that are in common to the list. So instead of just looking for all of the factors, I can just make a factor tree and use my prime factors to find the GCF. So in this example, I'm going to look for the GCF for 18, 42, and 54. So I'm going to start by finding my prime factorizations and making factor trees. So starting with 18, I know that's going to be 2 times 9, and 9 breaks down to 3 times 3. So for 18, my prime factorization would be 2 times 3 times 3. And then I'm going to break down the 42. So 42 is 2 times 21. 21 is going to be 3 times 7. So for 42, my prime factors would be 2, 3, and 7. And now let me break down the last number, which is 54. So 54 is 2 times 27. 27 is 3 times 9. And 9 is 3 times 3. So for 54, my prime factorization is going to be 2 times 3 times 3 times 3. Now I'm going to look for the prime factors they have in common. So each of these lists has a 2 in common, and each of the lists also has a 3 in common. That'd be the common prime factors on those prime factorization lists. If I find the product of the prime factors they have in common, I find my GCF. So in this case, the product of the 2 and 3 makes our GCF 6. So here I'm going to say the GCF for 18, 42, and 54 is going to be 6. Okay, now just organizationally, I want to show you another way that we can visualize and see the connection between the factors in our number and the GCF. It's probably not the way I would find the GCF, but it will become helpful when we get to the next topic, and that's using a Venn diagram. So the product of the numbers in the intersection of a Venn diagram of the prime factorizations of each integer will illustrate the GCF perfectly. So I'm going to find the prime factorizations for another set of numbers here. In this case, we're looking at 36 and 48. And then I'm going to make a Venn diagram that shows the connection between those prime factors. And in the intersection, I'm going to find my GCF. So let me start with the 36. 36 is 2 times 18. 18 is 2 times 9, and 9 is 3 times 3. So I've got 2 times 2 times 3 times 3 for 36. Okay, and then I'm going to break down my 48. Pretty sure I said change to red. Thank you. Okay, so if I go to break down 48, I've got 2 times 24. 24 is 2 times 12. That's 2 times 6, and then 2 times 3. So I could say 48 is 2 times 2 times 2 times 2 times 3. Now I know that we can write those prime factorizations using an exponential notation, but actually I want those factors to be separate for the visual that I'm going to show you next. So what I'm going to do now is make a Venn diagram for these prime factors. So one circle for my first number, 36, one circle for my second number, which is 48. So I'm going to put 36 here, I'm going to put 48 here. If I was making this Venn diagram, the overlap in the Venn diagram would be the factors they have in common. So what's in common to these lists? Well, they have a factor of 2, they've got a second factor of 2, they both have a factor of 3, and those look to be the common prime factors. So in my intersection, I would have a 2 and a 2 and a 3. And then I have a leftover factor of 3 in my 36. And I have a leftover factor of 2 and 2 in my 48. Now just to double check the math here, if I multiply the 3, 2, 2, and 2 that I see in my 36 circle, sorry, not 2. There's a 3, 2 2s, and another 3 in my 36 circle. I get the product of 36, and then I have the 2, 2, 3, and then the two more factors of 2 in my 48 circle, and I get that 48. Okay, now, again, the intersection, the factors they have in common, the same thing I identified in that previous problem, they just show up really nicely in our intersection for our Venn diagram. So right here, that intersection, that's where we're seeing that GCF. So again, the GCF here for 36 and 48 is going to be 2 times 2, which is 4, and 4 times 3, which is going to make 12. 12 is the biggest number that will divide evenly into 36 and 48. Again, I'm not going to probably make a Venn diagram myself to find the GCF because I can see in my prime factorizations I've already got the answer the same way I did in that previous problem. But it's just another way to illustrate it, and sometimes those visual illustrations are super helpful for our students. Okay, now the good news is we also have technology that will calculate greatest common factors for us. So I just want to show you real quickly how to do this in Desmos. So a calculator, always a great tool in Desmos, which my work is kind of colliding here. Sorry about that. In Desmos, you're going to select greatest common divisor from the functions catalog, from our functions menu, and then you're going to input your list of integers separated by commas. It'll look a lot like the notation I've been using here, and I'll show you right now. So for example, if I want to find the greatest common factor or greatest common divisor for 120, 200, and 144, those bigger numbers, I know how to go through the process. I don't want to, okay, if I have a calculator that can do it for me. So I'm going to go to my functions catalog here, scroll all the way to the bottom, and you're going to see GCD, and that's what we want, greatest common divisor, which is our greatest common factor. And then I'm going to put in my numbers separated by commas, so 120, comma, 200, comma, and then 144, and it calculates my greatest common factor. Greatest common divisor is 8. So super nice to be able to use that technology to get that answer. So we have the greatest common factor, again, for 120, 200, and 144 in this case equal to 8. 8 would be the biggest number that divides evenly into those three numbers. Okay? So again, lots of practical applications for finding greatest common factors. We do a lot with GCFs in algebra. We're going to be using greatest common factors in our work with fractions, but I just wanted to show you a few more places where they could apply. So problems you might be able to solve with your students. So let's look at a few. For example, Angelica is planning a party for her daughter. She has 49 candy bars and 42 fidget toys to make party favor bags. She wants to use all the candy bars and fidget toys, so 0 leftovers. What is the maximum number of identical party favor bags that she can make? How many of each item is going to be in each bag? So when we get to the next topic where we start talking about least common multiples, and then we've got them in conjunction with greatest common factors, they sometimes get mixed up. So you want to make sure that when you're looking at a greatest common factor problem, you're looking looking for greatest common factor, we're looking for something that divides evenly into our numbers. So in your problem, if you are dividing up your numbers, you're generally going to be looking for your greatest common factor. So in this case, let's go ahead and find it. And I'm going to use the calculator because I have it. Let's find the greatest common factor for the two numbers we're looking at here, which is 49 and 42. Again, unless you can see that it's 7, that would be great. So I know that my GCF here for 49 and 42 is going to be 7. What does that mean for this problem? So we can divide these toys and candy bars into 7 equal or identical bags. So we're going to have 7 identical bags, and it says how many of each item is going to be in the bags. So in these 7 identical bags, let's go ahead and divide the 49 candy bars into the 7 bags. So if we take that 49 and divide by 7, then we're going to get 7. So this is going to be with 7 candy bars. And then if we take our 42 fidget toys and divide by 7, then we get 6. and this will be with 6 fidget toys. And now we've got our answer. Okay, so we're dividing into 7 equal bags. They're going to be identical. We're going to have exactly 7 candy bars in each bag, exactly 6 fidget toys in each bag, so each bag has exactly 13 items and the same amount of items. It's the only way to do this if you're making party favor bags, right? You don't want one kid going home and finding out that he only got 12 things and the buddy next door, or maybe it's a younger sibling got 13 or 14. Like, this is not fair. So I want to make sure we're dividing into identical bags. So 7 bags with 7 candy bars and 6 fidget toys in each. Okay? Not too bad. Let's look at another example. You've got an art teacher that has 120 milliliters of red paint, 156 milliliters of blue paint. She wants to use all the paint, so no leftover, to create as many small tubes of purple paint as possible. So if you haven't done art in a while, when you mix blue and red, you get purple. So she wants to make these small tubes of purple paint using the blue and the red that she has. Now she wants to, again, use all the paint, so she wants any leftover paint, and she wants all of the tubes to be the same shade of purple. So however much red and blue you put in each one needs to be exactly the same for all those shades of purple to be the same in her tubes. So how many tubes can she make? Again, you're dividing the paint into smaller tubes. So let's go ahead and start by finding our GCF. GCF for the 120 and 156. Again, I'm just going to let my calculator do the heavy lifting for me here. So 120 and 156. So my GCF is going to be 12, which means I'm going to be able to make 12 small tubes. So 12 tubes of purple paint are going to be made. And it also asks how many milliliters of each tube will be in that paint. So I'm going to do the same thing I did in the last problem. Let's take the 120 milliliters and divide it into the 12 tubes, and let's take the 156 and divide it into the tubes. So let me divide this one. 120 divided by 12 is going to give me 10. So there's going to be with 10 milliliters of red paint. And maybe I should have color coded my my writing with the paint colors, but it's too late for that. That ship has sailed. And then 156 milliliters of the blue, so let me divide that by the 12 because we're dividing it into 12 tubes. So 156 divided by 12 is going to be 13, so this would be with 13 milliliters of the blue paint. Okay, so each one gets exactly 10 milliliters of red, exactly 13 milliliters of blue. We've got exactly 12 tubes to make, nothing left over, all the same shade of purple, so perfect. All right, let's look at one more. Samantha, actually it's 2 more, but one more that's similar. Samantha has 2 pieces of fabric to use for a project. One piece is 72 inches long and the other is 90 inches long. For her project, she needs strips of fabric of equal length and as long as possible. She also wants to use all of the fabric, leaving no waste. How long should she cut the strips of fabric? And how many strips of fabric is she going to end up with all together? How many will she be able to cut? So again, you're dividing this fabric into smaller pieces. Let's find the greatest common factor for the 72 and the 90. Again, if you could see it, awesome. If you need your calculator, that's totally okay too. So for 72 and 90, it's going to be 18. And now I know I'm going to take my 72 and divide by 18 and take my 90 and divide it by 18. So how long should she cut each of the fabric strips? Again, this is going to be 18 inches. So each strip will be 18 inches long. And how many strips is she going to be able to cut? If you take the 72-inch piece of fabric she has and divide it by 18, 72 divided by 18 is going to be 4. So she's going to get 4 strips from the 72-inch piece. And then we're going to take the 90-inch piece and divide that by 18. And that's going to be, what, 5? Let me just make sure I'm not mathing that wrong. 72 divided by 18 is 4. And then 90 divided by 18 does make 5. Okay, good. I can math sometimes. So she's going to get 5 strips from the 90-inch piece. And it says how many strips is she going to be able to have total. Well, we can get that now. So that is going to make 9 total strips that are as long as possible and all equal in length. No leftovers. Perfect. Okay, so again, the key here is you're dividing something into smaller portions. And if they're equal in size, length, capacity, whatever it is that you're looking at, it's generally going to be a greatest common factor type of problem. Now I got something a little more interesting here. It says the greatest and only common factor of 3 numbers is 7. The product of their remaining prime factors is 30, and each number is greater than 10. We're going to, based on that information, try to figure out the 3 numbers that are being described in this scenario. And to do this one, I'm actually going to use a Venn diagram because I think it's very helpful in illustrating the numbers. So I've got 3 numbers. I'm going to make my Venn diagram with 3 sets. First number, second number, third number. I know you're jealous of my ability to make a crappy circle turn into a perfect one. If you had an iPad, you too could enjoy this luxury. So I'm going to call my numbers A, B, and C because I don't know what they are. So I know that the greatest common factor for my 3 numbers is 7. It's also the only common factor. So in my picture, my greatest common factor for all 3 numbers is 7. That's going to go here. And because it's the only common factor, that means that there won't be anything in this space, or this space, because there's nothing else in common to my 3 numbers. So I know those are going to be empty. Now it says that the product of the remaining factors is 30. So let me break down that 30 so I can see what those prime factors that are remaining are. So 30, if I break this down, is 2 times 15. 15 is going to be 3 times 5. So I've got remaining factors of 2, 3, and 5, and I have 3 remaining places where I could put those factors. So without the next bit of information, I really could put these anywhere, but it says in the next bit here that each number that I'm looking at is greater than 10, and I wanted that to be a nice line. So each number is going to be greater than 10, which means I'm going to have to split these factors up. Like they can't all go in B and leave this blank, because if I left this blank or this blank, then my number would just be 7. That's not going to work. So, and I couldn't put like the 2 here, the 3 here, and the 5 here. Again, leaving this number as just a 7, not big enough because all of my numbers have to be bigger than 10. So they're each going to have to get one of these factors. So I'm going to put 2, 3, and 5, split those up. And now I have 14 as one of my numbers. I have 35 as one of my numbers, and I have 21 as one of my numbers. Those are all bigger than 10. The product of the remaining prime factors, 2, 5, and 3, does make 30, and they have a GCF of 7. So now I can clearly see again, the Venn diagram was a clear way to show what my numbers would have to be. So it sort of unfolds nicely in that picture. So my 3 numbers are going to be, the numbers are, what did I say, 14, 21, and 35. Again, they've got a GCF of 7. They're all bigger than 10, and the product of the remaining prime factors that they don't have in common makes that 30. Okay, so I'll see something similar to that in your homework. Hopefully it's a good opportunity for you to play with the Venn diagram a little bit. All right, so I think you've got enough to go on. If you have any questions, reach out. Until next time, take care.